Thank you all for coming, and welcome to this workshop that is organized in the framework of the chair in critical embedded systems that is funded by Asian Alstom, and that is supported by the consortium Contribute. And so it is my pleasure today to welcome Pierre Meunier, who is Director of Innovation at Alstom. And we'll talk today about embedded systems and the criticality of embedded systems within the rail environment. So let's thank him for coming.
Okay, thank you, Christelle. Can you hear me properly? Yes, the sound is okay. So the presentation will be fully in English. The slides are in English, but as you will see, there is nearly no text on the slides. I will speak in English. There will be one short video that with French subtitles, but I don't think it will be an issue. So this is not a course, as I said when I arrived. It is not a conference. We decided to call it a workshop. Why? Because you can stop me at any time. I do not pretend that what I selected to say or to show to you is complete enough. So if you have questions, if you want more details, just raise your hand, do not shout, and I will try to answer at any time. So as Christelle said, this workshop is organized in the context of the chair that we have here in UC Louvain, dedicated to critical embedded systems. And the purpose of this workshop is to explain why these critical embedded systems are so important in the context of mobility, but also in the domains of the industry. And we decided to do it in two steps. We'll first start today with the railway applications, and we'll have a second workshop in autumn, introducing the application of embedded systems in the automotive industry. I hope you will be ready. Okay, so this was the context. So what's the agenda for today? Some of you, I think, visited Alstom some weeks ago. Did you? Yes, but not all of you. So there's a very short reminder about Alstom, who we are, what we do, especially here in Belgium. I've removed plenty of slides with all the figures, just explain technically what we do. Then the second topic is to try to explain the link between critical systems and the rail industry. I often get the question that I don't understand. What do you mean? Why do you need digital systems to operate a rail mobility system? Why? So I will try to answer that question. The second question is really about critical embedded system. And the first word is important, critical. What is meant by critical? How does it work? What does it mean in terms of technology? We'll try to explain that with the time that we have today. So a few words on Alstom as an introduction, which is our mission. Our mission is to create new mobility solutions, contributing to the decarbonization of the mobility. So the target is not to eliminate the mobility, but to modify it. And how do we do that? We do that by developing solutions that move on rails. It goes from light rail, like tramways, up to heavy rail, like high-speed trains. So I guess that one day, at least, you must have been using an Alstom mobility solution, either taking the train this morning to come to Louvain or going to Paris with the Thalys or else. So you see that the portfolio is quite large, and it is even larger than 2-3 years ago, because at that time, Alstom decided to buy the railway branch of Bombardier. So Bombardier and Alstom in the rail business are now only one company. So this slide is important because the second section will make the link with what we'll be talking about today. We have typically three kinds of activities within Alstom. The first one on the left is, let's say, the conventional, historical activity of the group, which is to develop mobility solution on rails, vehicles, but also the infrastructure that goes with it, catenary system, signaling. We'll talk a bit about it. But it represents nowadays typically 1/3 of the business. The orders of magnitude are 1/3, 1/3, 1/3. So this decreases the historical content of the activity of the group. The second section is the digital solutions. And this is exactly what we are going to talk about today. Everything that is needed to operate a rail mobility system, and that uses digital solution or embedded system. So I will not enter into the details now. And last but not least, services. Typically, our customers buy our solutions to use them for a period of up to 15 years, at least 30, even more than 50 sometimes. So this requires a specific organization. You need the processes, you need the spare parts, you need to be able to repair or to upgrade a system, including digital ones that have been developed sometime years and years ago. So it's really a typical characteristic of our business. So what do we do specifically in Charleroi, where I come from? So we are a site of roughly 1,400 people. It's growing and growing, and we are hiring typically 10, 12 people per month. And we have a high mix of nationalities. The current indicator is 29, but it is varying a bit continuously. And it's something that we are proud of, that mix of nationalities. So English is our working language because of that mix. And we like it because it's really a mix of culture, of different point of views to work on different topics. So it is something that is really encouraged. And what is fun in what we do, and that we tend to appreciate, is that what we develop, as you will see, our site in Charleroi is a development center, is being developed there, but deployed all over the world on all continents. And we have continuously a large number of projects worldwide that are using the products, the solution developed in Charleroi. So what do we develop? What do we develop? What is unique to this Alstom site in Belgium is the fact that we have two types of activities. They are both connected to electrical engineering. They both include embedded systems and even critical embedded systems. One is more dedicated to energy conversion, French, and the other one is more dedicated to the digital systems per se, so it's our digital solution. On the left side, our core activity is to build energy converters. So a big box that takes electrical energy at the input and that generates electrical energy at the output in order to supply the load of a train, of a rail mobility system. And along the time, we also developed a number of recovery solutions, where, for example, we can recover the braking energy of the train and store it somewhere along the track in order to give it back to another train later on. Signaling, you will see a lot of details in the presentation, and this includes driving automation. You will see that automating the mobility of a train is something that is quite common, is quite established in our domain, and I will explain why. So the two types of activities are active. Some examples of projects very quickly, and then we'll move to the core of this workshop. This is an example of a project that is being deployed in Belgium. These are the new trains for SNCB. You may have used one of them this morning. Double layers trains with high capacity, with more space, more comfort. But these trains are quite powerful, efficient, because they can reach a speed of 200 kilometers an hour. So the power conversion of that train, All the digital systems of these trains have been developed here in Belgium and are deployed on the trains that are manufactured, assembled in our second main site in Belgium, based in Bruges, which was historically the Bombardier site. Another example, more local for those who go sometimes in Charleroi, it's a renovation project. It's a bit unique because we are building new trams with old trams. They have been built by the ASEC and Bourgeois des Villers in the 80s, and they are completely renewed in order to extend their lifetime. And it is a way to have new vehicles with a reduced investment to improve the accessibility for people in wheelchairs, for example, which was not possible in the previous generation. Another one, different, nothing to do with the rolling stock of the vehicles, but with the infrastructure. And as you will see in the presentation, the infrastructure plays a key role in the digital system of rail mobility. This is called a location case, loge in French. So location case is a small bungalow, small building that you place along the track, and it is full of electronics, of digital systems that take part into the signaling, into the operation of the railway system, and it is connected to what we call the track objects, for example, the signals with the lamps, the point machines that will move the points. All these equipment have to be connected to a digital management system, and this is done by using those distributed systems, and they are distributed mainly to reduce the length of the cables that we install along the track. So this beast is connected through a digital network based on fiber optics and gets power, and everything is converted into that cubicle. And we have supplied roughly 2,000 of them here in Belgium. So if you take the train in Belgium, if you look through the window, you should see them along the track. Last example, speed control. As I will explain later on, if you want to achieve the safety objective of the rail mobility system, you need to enforce speed control. You need to protect against mistakes, errors done by the driver. Otherwise, you cannot reach the safety objective. And there are very sad examples of accidents that occurred 15 years ago. So we are developing these safety monitoring and speed enforcement system. There is a European standard that allows us to deploy the solution developed here in Belgium, really worldwide. And we currently have typically 3,000 trains that are equipped with the speed control solution that has been developed here in Belgium. So this was about Alstom. It was quick. I promised that I would make it short in order to focus on the content of today's workshop. Any question on what I've shown up to now? So I will now ask you a question. There is one key reason why you need a digital system to operate a rail mobility system. Do you know which is this reason? It's a technical choice that has been made one day, which is driving nearly everything.
Signaling?
Signaling is part of the solution. It's not the problem.
Evolution? The evolution?
Right? Safety is a requirement.
Modularity?
It's not the root cause.
Error exclusion?
It's part of the problem, but it's not really the root cause. The root cause is mechanical. Some engineer.
Yeah, of course. But I don't know the answer.
Okay. This is the answer.
Okay.
This is the answer. The rail mobility system is based on metallic wheels, on metallic rails. This is the core of everything. And do you know which is the surface, the contact surface here that you have between the rail and the wheel? You have an idea?
Centimeter square.
Yeah, yeah. It's the size of a stamp. You could choose a different stamp, but it is the size of a stamp. So the contact surface between the wheel and the rail is extremely limited. And it has a lot of advantages. This choice was brilliant. We should not blame anybody for this choice, because it's a very robust way to have a heavy vehicle on a track. It's very robust. And if we had tires, it would be a nightmare. Some tried in Paris for the metro, but it was not a very good idea. It is guided, and it works really well. When you try to deviate, there is a good experiment that is a test bench that is available here at UC Louvain. Ask your professor or Alexandre to see it one day. It's very interesting. So it's guided. And the low rolling resistance is such that when a train is moving at a given speed, if the track is flat, you basically do not need any energy to maintain the speed. It goes on and on and on. There's nearly no loss at the contact between the wheel and the rail. So it is an excellent choice. This is why the train mobility is so green. It uses electrical energy on one side, but you don't need energy at all to maintain the speed. It's not true. Of course, you know that there are losses and there are gradients that you need to compensate, but it's a brilliant choice. But it has consequences. It has consequences. Imagine your car with flat tires. What happens? You have problems. You have difficulties to accelerate, and you have difficulties to brake because you have a slip and slide effect. Just to take an example, if you compare the braking distance between a car and a train with a similar speed, it is multiplied by 10 for a train. So this choice, as you will see, has a number of impacts. Because of this slip slide effect, you need, in order to have a performant rail system, digital solutions. Why? Because on top of this choice, there is a willingness to have something that is excellent, brilliant in terms of performance. If I look at high speed, you want to operate a train at 350 kilometers an hour in operational condition. This is the commercial speed of a Thalys, for example. And on the other side, if you look at the urban mobility in a metro system, you want to have a lot of trains, one after each other, into the metro, for example, of a busy town, because you need a high capacity. So the trains are close to each other, but they have difficulties to brake. You do not always have the visibility. For example, one train every 90 seconds, it is very low. Is what you achieve in a typical metro system. And we want to achieve that performance despite those characteristics of the contact between the wheel and the rail. And on top of that, this is a very sad picture. This is something we never want to see as an engineer in the rail business. This was the Boesingen accident in 2010, so 15 years ago. A very sad day for us and for the rail industry, for everybody. There is this objective of safety, which is so high that in order to achieve it, on top of everything that I have listed before, you also need a digital system, because that objective of one serious accident in Europe per year is very, very, very high. Serious means seriously injured or dead people. Once per year in Europe. Extremely high, and I will explain later on what it means in terms of technical design. So at the end, this historical choice of using metallic wheels on metallic rails, plus the willingness of achieving a very high performance, trains close to each other, high speed, and high level of safety, all that makes it completely impossible without the embedded digital systems. It does not work. It cannot. Yes, you had trains in the past that were running without digital system. I will show a few examples of solutions that were put in place, but it was one train or on a very quiet track at very low speed. It was completely incompatible with the objective that I've shown now. So where do we have digital or embedded systems in a rail mobility? So to explain that, I will use this picture, which you can find on the Alstom website, but it was good to really give you the big picture and explain which are the components, the elements, or the functions that we need. Because as you will see, there are typically 6, 7 different embedded systems in order to allow the train operation. So the first one is traction. Traction is the system that will allow you to apply power to the wheels and allow you to move the train. Why does it need a digital system? As I said before, if you want to accelerate and if you have metallic wheels or metallic rails, it's tough because if you put too much power or too much mechanical effort on the wheels, you will not move. You will simply destroy the wheels and potentially the rail. There are very funny videos of steam engine trains trying to accelerate, and you see the driver looking through the window at the wheels and the rails being destroyed, and the locomotive is not moving at all because he has to regulate the power applied to the wheels. So if you want to do that and efficiently, if you go today on a modern train, the speed will grow up very efficiently. If you take the Brussels metro, for example, it's a very good example, which reaches 70 kilometers an hour in a few seconds, because we are trying to get really the optimum. And that optimum requires a kind of regulation process that can only be achieved with digital solutions. Second one is signaling. You see this portion on board of the train. Signaling is the digital system that will ensure the safety. It's one of the digital system within the rail system, but it's a key one because it's the one that will ensure safety integrity that I've shown before, one major serious accident in Europe. It has a component on board of the train, but it's a more complex system. There are pieces along the track. You will see which one in a minute. It needs to be supervised. So the traffic management system is centralized. There is someone or a few people that are operating the railway in areas globally over the country in order to make sure that the trains are on time and to manage degraded modes when they occur. So it's a complete system. ATO, automatic train operation. So it's something that exists today. It's a function that is available and that allows the train to operate autonomously. And it has, as you will see, it will be described, 2 subsystems, one on board of the train and one in the control center, because an autonomous train needs to get data from a data center in order to know which is the optimum speed at which it needs to drive. TCMS, Train Control and Monitoring System. It is the PLC, Programmable Logic Controller, that is managing the train. You have to be able to open the doors, to manage the direction of movement, all those functions, all the items that you have on board of the train are operated by a digital system with MMIs for the driver. It is connected. It is a distributed system, so you have a digital network or multiple at the end, digital networks on board of the train with CPUs and with IOs, remote IO module. RIOM on the drawing is an IO controller that will exchange data over the network with the central computer. And all that is connected to mechanical drivers, to inputs for different sensors. So it is an embedded critical system. It's a physical, cyber-physical system with a digital portion connected to the physical real world. And the train will not work if you do not implement such a system. And on top of that, you know that the availability of the trains is key. Why? Because typically a train is operated all day long, and you just have a few hours during the night where you can perform maintenance. Train can go back into the depot, and you have typically 4 hours in order to repair a failure. But to do that efficiently, you need to know in advance which are the spare parts that you need, which are the skills that you need, which are the tools that you need to make sure that the train is back in operation for the next morning. So modern trains perform self-diagnostics and send information over the air to the maintenance depot in order to operate, in order to optimize the availability of the trains. And you have control centers, for example, for a given country where all the trains are connected and you can see their state of health, monitor what are the issues, and plan the maintenance operations. All that is absolutely essential to achieve the availability target. It is part of the performance of the rail mobility system, because train operators can have spare, but they cannot double their fleet just to manage the maintenance operation. Do you know what this is?
Uplink.
It's one of the functions, yes. But make the link with what we are talking about today.
Systems that need to communicate, connection.
Correct. So this is the network connector. Yes, of course, there's a mechanical coupling. But a train is made of different pieces. Each piece has a digital system, an embedded digital system. And when you connect cars or consists pieces of train together, you are building a new communication network that you need to reconfigure. And it is as critical as making the mechanical coupling. Today, we are focusing on the digital systems. So I will say that it's the most important need in that case. So a train is made of subsets, a vehicle, a train set, a train, and it can vary along the time, along the day. And you need to reconfigure that system depending on how you assemble, how you couple the pieces together. So when you couple a train, you create a new network connection and you have to reconfigure your network or even potentially networks if you have more than one on board of the train. So now you will see this piece a bit differently when you will see 2 trains coupling in a station with, yes, it's a network connector. Last subsystem, passenger address or passenger information system. In the modern trains, it is even more developed than before. If you take the new M7 train, you will see you will have a lot of detailed information on the next stop, on the impact of potential delays on the time of arrival, the train connections that you will have in the next stations. That is important for the comfort of the passenger. So this system is also connected to the control center. It gets data live over the air, and it provides information to the passenger. It's also the system that will allow the train manager to give you information, voice information, for example. It is also a digital system. that is broadcasted all over the train. And again, if you have one train manager, if you have coupled two trains together, you need to make sure that the voice can be heard all over the train. So you need to reconfigure, and it has some level of complexity. And you need to make sure that it is not heard into a train. So it's also an essential piece of the system. So it's called public address or passenger information system. So it's another embedded system within the train mobility system.
The connection is wireless.
It is wireless. You have a wired connection within the train, and you have a connection over the air. Typically Wi-Fi in urban applications, or in metro applications, and GSMR, or when you are using, when you are using, or in the future 5G, when you are in a rail application. So this is the big picture. You see all the pieces that I've shown. I've added the network. In fact, these are networks. It's a bit simplified. Everything that I will show today is sometimes a bit simplified, but it gives you the feeling. So all these subsystems are part of a wider digital system, and you need to make sure that everything is working properly together. Traction, the signaling, the TCMS, everything is connected, the digital maintenance system, and needs to work all day long with a very high availability and reliability. So these are the digital embedded system that you have in a rail mobility system. In short, these are the different systems. Now we will focus a bit more, each of them, not all of them, and then we'll talk about critical systems. So the first thing is to make sure that the train can move. Remember the example of the steam engine locomotive that is not able to move at all. So in order for the train to move, you have this kind of big power converter. It's big compared to the digital embedded systems. It's typically 1 ton, let's say, or 2 tons, and it goes on the roof. Picture, yeah. It can go on the roof of the train. If it has a round shape, it means that it goes on the roof of the train. If it's a rectangle, it goes behind, not behind, under the train, under the floor of the train. And it's an energy converter. So it is a power converter that will take energy from the catenary, typically, if it's an electrical supply or a third rail in some application. And in a typical arrangement, you have 2 different converters. One is dedicated to the traction, so we will provide electrical power to the motors of the train in order to make the train move. And you have an auxiliary converter, which is there to supply all the rest of the train, the light, the air conditioning, your computer while you work to review your embedded system, of course. So all that is done by power converters. And as I said before, these power converters cannot work without digital solutions. So this is a picture that was taken a few months ago in Charleroi. It's a typical product that we design. If you look here, you will see this is a computer. This is a computer with a lot of I/Os, currently parallel I/Os, which is in fact the brain of such a system. This is the power conversion unit with the so it's a solid state converter that needs to be driven. So if you look at this, it is an embedded system. You have a CPU with I/Os. You have parallel connections to sensors because you have voltage current sensors, and you have outputs to drive the solid state switches of the power converter. And it has a software with different layers, an application layer that will change depending on the circuit diagram of the power converter. So it's an embedded system. And it can be critical. It can be critical because there are some functions for which you need to guarantee some reaction times, for example. If you create a short circuit, yeah, by activating two switches at the same time, you could create a fire. So you need to react to stop as fast as possible. So the cycle time of the current generation is 232 microseconds. So this is the cycle time of the overall embedded process. So the full application is executed within that cycle. We have been sensing all inputs, and we have updated the status of all outputs within that time. Okay. Rather fast, but this is to give you an order of magnitude. So this technology is evolving. What I've shown before with this type of parallel architecture is becoming obsolete. In these power converters, like on the trains, we are deploying digital networks. So modern converters have an embedded network that is based on Ethernet technology with a slightly different protocol, which is an industry standard. It's called EtherCAT, which has the benefit of guaranteeing timings among the network. So it's a process in which you have a master and slaves can take a portion of the data over the Ethernet message and insert back a portion of the message. Everything goes into a loop. So you have one message going from one subscriber to the next one. And this will allow, yes, the timing is there, to accelerate the system and to divide the cycle time by a factor of 2. So 116 microseconds will be the new cycle time of this embedded system. And on top of integrating the network, it's allowed to simplify all the cabling within such a subsystem. As you will see here in the drawing, I know there are some electrical engineers, the new power circuits are getting more complex because the trend in power electronics is to increase the number of solid-state switches in order to go for modular architectures, to cope with the characteristic of the new components. You need more, you need to put in series in parallels. So it means that you increase the number of outputs that you have to manage with the critical system. You have more switches to drive. You need more outputs, so it would mean more cabling, more complex cabling into the system. If you have a network, and if you have distributed I/Os all over the box, you can do it more efficiently. You can decrease the number of inputs and outputs more efficiently. So a power conversion system in a train is a critical embedded system. Not as critical as signaling, but critical because there are some critical functions in it, but for sure an embedded systems, which requires a lot of digital competencies. It's really at least 50% of the complexity of such a system. And this is just required to allow the train to move with the performance that I've mentioned before. For the train to move autonomously. So, do you think that trains have been autonomous for a long time, or is it something recent? 5 years, 10 years, 20 years, 50 years.
Depends on what we call them.
There is still a driver in the train, so for me it's not autonomous.
Okay, I accept that, but it's not quite the point.
Maybe it's just a supervisor for the train then. Like he just sees if everything goes correctly.
Okay, I will then explain. So it's quite old, in fact. The first autonomous train was put in commercial operation in Singapore in 2003. It was designed by Alstom without any driver. It's fully autonomous. If you take the metro in Paris or soon in Brussels, you will see that there is no driver on board of the train. It's fully automatic. It's a metro. It's a metro. And it means that it is also operated as a loop. So it goes to one end of the line and comes back. All the trains are the same. Shape of the train, the position of the doors in front of platform screen doors is constant. So it's much easier to make a metro autonomous rather than a line train like SNCB. It brings some complexity, but there's no driver. Want to do that on a train on a conventional line, it gets more complex because the trains are different, the events that can occur on the track are different, because the schedule of the train can be adapted along the day. It was planned to go on platform 3, but platform 6. So it makes it more difficult. And 4 levels of automation have been defined. I think it's 5 in the car industry, but it's the main, more or less the same concept. It goes from 1 to 4. 1, the train is just protected, so 0 means there's nothing. The train is just controlled, supervised in terms of speed, and 4, no driver, everything is done automatically. And we would like to reach up to level 4. So how does it work? And I will explain why in a minute. So how does it work? So you have a computer on board of the train. The computer is there to monitor the speed, and you want it, in fact, to activate the train and define which is the optimum speed profile, in fact, the speed at which you want to drive the train. So the train will connect the control center and receive a timetable. It will tell the train, this is where you have to stop and at which time. Because this is what is essential to arrive on time. You need to know which is the timetable. So the onboard computer will calculate the optimum speed profile depending on the stopping points to make sure that it will arrive exactly on time. Not in advance, not too late. So the time of arrival and departure is fully guaranteed. So the computer will calculate it. So this computer will then activate the system that you have seen before in order to activate the traction, regulate the speed of the train automatically. If you want to go up to GOA4, so full of automation, of course, you need to completely replace the driver. The driver has some responsibility today. He's looking through the window and must react on some situations. You need to transfer that responsibility to the onboard computer. So you need to sense the environment. So you need to fit the train with all the sensors that we start to have on our modern cars, in fact, in order to sense the environment and make sure that anything that shall be detected by the driver will be detected by the sensing system in order to stop it. And you have seen the people in the track. You need to detect that people are on the track and brake the train, which is today the responsibility of the driver. I'm not sure you will be able to stop on time, but you must brake. So what is the main objective of train automation? The main objective is not to get rid of the driver. It's not to get rid of the driver. That's not the target. The essential targets are in fact 2 targets. The first one is to improve the punctuality, as said before. The computer will drive the train in order to get to the station exactly on time. And it improves the capacity of a rail system. Why? It's not obvious. It improves the capacity because if you look at the train timetable today, you need to have margin because train drivers will not all drive the train in the same way. Like when you drive a car, we do not all drive in the same way. To arrive on time for the workshop at Charleroi, some have been driving extremely fast and braking at the last minute. So at the lower speed and still arrived on time. And on top of that, if you optimize your speed, you improve your energy efficiency, and you save your hardware, your vehicle, because you're using less your brakes and provide less, let's say, mechanical effort. So the two main objectives of autonomous trains is to increase the capacity, because this is a challenge. We want more trains on the existing tracks, because if you need to build more tracks, see with the RER in Belgium, what it takes, you need to expropriate some people, you need to build new tracks, it takes a lot of time. So the idea is to have more trains on the existing tracks. Digital systems with train automation can achieve that without any syllable, by eliminating the margin into the timetables. And the next objective is to achieve energy saving. And I've got some figures. So this is the energy consumption profile of a stopping train. So a train that stops at every station. One of the curve, the one with the peak, or the peaks, is the one of a real driver. Was a professor from SNCB, so he was very skilled. But still, the computer did better in terms of energy conversion. They all arrive at the same time at the stops, but the energy consumed by the train when driven by the computer was much better than the peaks that we had with the human driver. Because the human driver is not able to make all the speed profile calculations with such an accuracy that the train computer does. And the train computer is informed regularly on what will happen in front of the train. The driver sees what he sees through the window and nothing more. So if you make the calculation all over the train trip, this was between Leuven and Brussels, you can reach up to 42% of energy efficiency, which is huge. There's no other way to reach that. You need the computer to do it. Yes.
Does the computer have full information about, let's say, what kind of wagons are attached to, so how much weight?
Yes. Yes. If you really want to achieve that optimum, you need to have such data. So the train characteristics are essential in order to optimize the calculation algorithm for the autonomous train, but also for the signaling to be able to brake the train. Yes, so yes. And it can vary over time. As I explained before, you can modify the configuration of the train. The wheel diameter can vary also, so there are some characteristics that will change over time. And that the computer needs to know. Yes. Any question on that? Yes.
I understand why it would be without then you are explaining that drivers are going to trains differently than to small variation. That's advanced train drivers, train or some way to drive, especially courses. Compared to just a regular traveling around the world.
I did not get your question.
Aren't there already requirements and requests to how the train drivers should try to train.
Okay. So it's a driving advisory system. It's called DAS. So yes, there are systems that provide information to the driver, provide recommendation on how to drive. Adapt your speed, give information on what will happen at the next stop. Yes, it exists, but it's only a piece of the solution because it's not coupled with the signaling. We do not couple the autonomous driving with the signaling that will in fact break the train. You don't have the full regulation of the speed. You need both to accelerate and brake on time depending on the safety conditions. So yes, there are recommendations that exist. It could even be on paper, or you can give a paper to the driver. This is the line, and this is how you should drive. But it's not connected, static information that will not be updated online, depending on the events, on the fact that a train in front of it will break, for example. There's no information on that. You cannot do it. So if it's not connected to the rest of the system, you cannot achieve the optimum, especially in integrated modes. Does that answer your question? So, yeah.
For the extension, if we couple the DAS to and feed it more information with real-time track information, signaling, etc., could we achieve a similar performance with human drivers?
If the human driver was able, as I said, to calculate the speed profile as the computer does, yes. But he cannot. But yes, if you give all the data to the driver, it's computing its speed profile, but he needs to know how the speed shall evolve in order to stop at the next stopping point. Regulate that in an optimized way. Did you ever try to drive a train?
So what I'm thinking is that we can, instead of giving static information of the driving profile, to use the give hints like heads up display, the driver saying, okay, in 2 seconds there is a red light, so you need to start braking now, and not require the driver to do calculations, because even I won't be doing calculations on how I need to drive my car to know that I am stopping 2 meters and not just 1. Let the computer handle the calculation, because that's what computers are made for. They compute stuff and way better than humans will do.
Correct.
But give hints to not have a static driver profile, but give the information to make that more dynamic and adapted to the system.
So the driver advisory system is working exactly as you described. So the basic system is to give a piece of paper to the driver, to the static. The driving advisory system is doing exactly what you described. The automatic driving system is doing that and is connected to the signaling that potentially will decide to reduce the speed of the train. So the best, let's say, regulation can only be achieved by combining signaling with driver advisory. And on top of that, if it's fully autonomous, the driver is not moving, deciding how to increase the traction of the train. It's done by the computer. That's the add-on. What you describe is a driver advisory system, a connected driver advisory system. It exists, but it does not achieve the optimum performance, because driving the train is still manual and it's not connected to the signaling that can potentially decide to reduce the speed of the train.
How close to the optimum are we in that situation?
It really depends. It will be in normal situation, and if something is okay, maybe that you will be very close to the optimum. If you have a very good driver, he knows the line by heart, he knows exactly how the train will behave, and nothing happens on the track, maybe that he will be 99% close to the optimum. But the system is made of degraded modes and expected situations, and this is where the computer is there. Yes.
Yes, to know how digitalize the train signaling will really improve the timing problem if the train company says that the timing problems come from the travelers.
Okay. So in an autonomous system, it also normally includes, it's a part of the solution, it includes the way you manage transfer of passengers between the platform and the train. And if you take an autonomous metro, you have, for example, platform screen doors on the platforms, which open and close in front of the train doors. And it is there really to guarantee that within the predefined time, your passengers will be on the train, will get out, and will get on the train. So that contribution of the traveler's behavior to the train delays, because some arrive at the last minute and block the doors, so you cannot close the doors, is improved by the platform screen doors, which is typically part of an autonomous system. If it is unmanned, there's no one on board of the train, typically you need the platform screen doors, and it's very complex for let's say railway applications rather than urban applications, because the doors are not always at the same position. So it's a bit messy to see. Okay, now I have a short video. This is to allow me to have a 2-minute break and drink a bit. This is about digitalization of the mobility. So we'll talk about data and how we can improve the mobility by the use of digital system. So it's really optimization of the system on top of what has been presented before. And then we move to the critical systems. This one is in French, I'm sorry. It's another break. Okay, so what can be the added value from data? If we have digital system all over the train, all over the infrastructure, this is full of data that is needed for the operation. But what can we do with this data? So here you have some examples of applications that are being developed on top of the core functions that I have described in order to further optimize the rail mobility system. Maintenance is obvious. If you collect data on how the system behaves, you can extract from this data some useful information in order to improve the maintenance. I've mentioned it before, modern trains are connected, they talk to the mobility center and explain what are the issues, even sometimes in advance. predictive maintenance, because you can observe deviations of some hardware characteristics. The operations and the energy management, you have the automation in order to optimize the energy, has been described before. You have conflicts that can occur. A failed train, for example, you need to manage it, you need to reorganize your traffic. Today, this is done by using the data collected potentially from all over the country. You know that in Belgium, it's a bit complex because you typically have two train networks, one in Wallonia, one in Flanders, connected through Brussels, you know, the Jonction Normandy, with 6 tracks, 3 in each direction. And if you have an impact on one side, how does it transfer to the other side? So you need algorithms at country level in order to optimize the reaction to such events. The city flow with mobility analytics, just to give an example, how to optimize the rail traffic in a situation where you have a reduced capacity due to a pandemic. It is a problem that we had during COVID, where we had to limit the number of passengers on board of the train. How do we do that? We add extra data to the regulation. We analyze the flow of passengers in the corridors. Security or cybersecurity monitoring, threat detection. These are typically technologies that we do not develop in-house, but they are implemented, connected to the rail operation system in order, for example, to stop the train in the stations if something occurs. So along the time, all these functionalities are being added to the system and use the available data. Operation statistics. More and more cities want to understand how the mobility system is operating, which is the exact achieved performance, so creating dashboards in order to understand where passengers go on board of the train, when they get out, how to optimize, in fact, the mobility system. So using, for example, capacity analysis, prediction, artificial intelligence, in order, I mentioned timetables. This is a solution of the past. Future mobility systems will be much more on demand. How can I adjust? Not completely on demand, maybe for trains, but today it is obvious that the existing timetables are not optimized. They are not optimized. Some trains are nearly empty, and at some peak hours, there are not enough trains. So this offering shall be adapted to the demand, to the needs of the passenger. This can be done by collecting the data and adjusting, for example, the timetables, depending on the needs of the passenger.
I think you answered my question on the slide, but I guess
That's why.
That's why I guess for predictive maintenance, we use for machine learning.
It's part of the available technologies, yes. It can be that sophisticated. Sometimes it's very simple, for example, when it's related to a deviation of a physical parameter that demonstrates that something is ailing. You don't need machine learning, it's just observing the parameter, measuring it to the pressure. But it could be as sophisticated as that.
But right now, it's not as common to do that in this field.
It's in progress. It's in progress. Yes, because you need to collect the data, you make sure that all the trains connected, and we have all trains that have been delivered 30 years ago that are not connected, or you need to add new systems on board, new ways of communicating in order to collect the data. Well, it's accessible, but to have it countrywide, takes time. Another example, we mentioned the delays by the passengers. Was one of the questions. So to optimize the passenger flow, maybe not on the main lines, but for sure on the metros. It's very frustrating when you are standing on a platform in Brussels or in Paris. You must have experienced that. The trains enter the station. And the car that stops in front of you is the only one that is fully packed with passengers, and there is room in the other ones. So you would like to know when to stand on the platform. This is completely possible today. And for example, we developed a system with lights on the platform, and the color of the light tells you where there will be space in the arriving trains in order to increase the fluidity of the passenger exchange. Another short video showing, let's say, the extreme of what can be done in terms of collecting data, and it's called a train scanner. Yes.
This might be a question, but for the system you mentioned before, with the lights, how do you deal with colorblind people?
Correct. No, it's not a stupid question at all. If you want to pretend that mobility is inclusive, you need to take care of that as well. So there has been solutions that have been developed with voice announcement, either directly on the smartphone of the people because they are connected to the system, or through the platform speakers. But it's a very valid point. If you want to make sure that people use more and more the rail mobility, you need to make sure that they have access to it. Another small. So that's clearly the extreme of what you can think about. You just have your train entering the depot, it goes through the scanner, and all the data are collected, even the data from systems that are not digital. For example, you can check the status of the wheels automatically and digitalize that information in order, again, to optimize the maintenance process. So that's called a train scanner. Now, the train is something, but the train drives on a track. So you also need to monitor your track, because if your track is not available, the overall system is not available. So again, there are ways to collect data from the track, from the rails itself, from the ballast, from the point machines. The current, let's say, well-known solution is this type of measurement train that is operated by Infrared in Belgium, managing the rail infrastructure. And the train is driving at night and collecting data, analyzing the status of the rail. It's quite advanced and it provides a lot of information, but you get information when the train is running and where it is running. So you can do better. You can do better. And as I explained before, we have plenty of embedded systems on board of the train. They are full of sensors. So why not using all the sensors that we have on all the trains in order to collect data to monitor the track? So this is an example. It was a project that we developed with students, in fact. It is in Norway. See Oslo over there. Because we had data from Norway, where we have a major project where we install our onboard computers on the train. And we use data that were collected by the onboard computer managing the speed of the train in order to detect anomalies on the track by finding correlations and detecting which were the data, the events that were collected that were abnormal. For example, here you see the Z-axis acceleration of the train, which showed that there was a problem, in fact, in the track stability at a given location. And it was a real one. And it was detected by chance. But the advantage of this approach is that you don't need, everything is software. You don't need to install any specific hardware in order to collect the data. The sensors that are already available are used. They are dedicated to a different function, but the data is deviated to a different algorithm that will provide useful information. So if you like this topic, we are proposing a challenge together with our friends from Eshin and with Tech, and this is during the Open Week that will take place in June. And in fact, it is a challenge where we would like to define ways and to help Tech to improve the operation of their mobility system. The example was that has been taken in Charleroi because we have the data for Charleroi, but it could work in Louvain-la-Neuve, of course. And the idea is to get rid of the timetables and to provide Tech with a system that will define in a dynamic way how they should provide trains, buses in their mobility system in order to cope with the real needs in the future. Because this needs to be planned a bit in advance. So there is a football match, for example, in Charleroi, and a lot of people will arrive with the train and they will need the tram to go to the football stadium. There will be an additional need for trams at that time of the day on that particular portion of the line. Today, nothing is being done. So people are walking or coming with their car. They don't know where to park because there's not enough metros. So if you like it, please register. The Professor Pelser can give extra information if needed on that challenge, and we'll be happy to work on it with you. So we'll now enter into the last portion of this workshop, which is really focusing on the critical aspects. And I will explain what it is, how it works, why it is important. And the main reason is safety. And starting from the safety objectives of a rail mobility system, there are a lot of technical choices that are specific, that are made. And this is what I will try to explain. So on this drawing, you see everything that we do not want to see to happen. These are the different types of accidents that then occur on the rail system. The head-on crash, the rear end. So head-on are two trains hitting each other from the front. The rear end, the train at the back is faster than the other one. The flank collision, that one is funny. Oh, it's my track. No, it was my track. So two trains on the same track. But it's something that can occur that you have to avoid. The simple, let's say, derailment. There is a damage in the track and the train will derail. So that damage needs to be detected. And the last one is Saint-Jacques-de-Compostelle, the accident that occurred in Spain, where there was no speed enforcement system that was operational, and the driver was distracted, not looking at the track. That's what we learned from the investigation. So he was too fast in a curve, and this is what happened. We were born at that time, so you remember that it was a real disaster with dead people.
I have a question.
Yes.
So this kind of accidents, do you have numbers in Belgium, like for derailments, even when there is no injured people? Does it happen often in Belgium?
No, it does not happen often in Belgium, but if I've shown this picture, Beuzingen, there was Pecro, there were a number of accidents. You were young, but you should still remember a bit.
Beuzingen, I remember. Really.
Yeah, it was not completely unacceptable. I've shown this slide for the objective, 1 serious accidents per year in Europe. It's demonstrated that we are not yet there. that they are still, okay, it's safe to take the train.
Mm.
If you take the statistics, you have a bit more than that, but still it's not enough. You have a few orders of magnitude to save. And every time there was an investigation, it demonstrated that the core was, let's say, human mistakes of different kinds. Lack of maintenance, lack of procedures, errors from the drivers, and that the deployment of a speed enforcement system, a digital critical embedded system, would have avoided the accident. Saint-Jacques-de-Compostelle is like that. If they have had the speed control system, the train would have been braking. And it was nearly installed, but it was not, and the crash occurred. So we are very close to that. It's extremely safe to take the train, you can relax, but still there are little improvements to put in place. It has improved a lot in Belgium. If you look on the location cases, the small buildings, it says safety first. It was the plan that was deployed by SNCB and Infrabel at that time after Beuzingen to make sure that the speed control system was put in place on all critical lines in Belgium. So there are still a few lines, a few less trains that are not yet equipped. So everything comes from this objective. I will give you a bit more details later on when I will explain how you can achieve such an objective technically. I don't have 2 days, but I will try to do it in a few minutes. This figure is important to have in mind. When you start from this top objective, you can calculate per function. A typical function of an embedded system is reading inputs, make a calculation, activate output, which is the integrity, to start from a number, so which is the integrity that you need to demonstrate for every function that your system will implement. So it will be expressed in failures that will lead to an accident or to something unsafe per hour. And this is what you get as a result. It can happen per function once every billion hours.
Is it the same value for the space industry?
Yes, for sure for the aircraft, for the system driving the aircraft, yes, it's a similar order of magnitude. We have similar objectives for the systems which are guiding the rocket, for example, or the destruction system of a rocket. You know, when a launcher has a problem, unfortunately, the only solution, because you want to manage where it falls down, is to destroy it. So you have the same integrity figure. But I will show example in the other industry. So that figure is important to have in mind, and I will explain how you can achieve it technically. But first, I will introduce what are the consequences of that objective on the rail system, functionally. Functionally, it leads to two different needs. One is called the interlocking, and the other one is the speed control. They have different objectives. You remember the 2 trains on the same track? It's not a matter of speed. You need to make sure all the trains reaching the end of the one in front. It's a mix of speed, but also a mix of trains being on the same track. So the first thing is to make sure that you do not have 2 trains on the same track. That's the interlocking function, which is a mechanical term. In fact, you will understand why in a minute, but it's the first thing that you need. But if you have that, and if you don't have speed enforcement, you are not protected against driver's errors. Remember, Beuzingen, the signal was red, but the driver didn't brake. So you need control on top. And the signaling system has these 2 core safety functions, interlocking and speed control. It appeared a long time ago. when we started to have more than one train on one track, when you had single tracks and potentially one train in every direction, you needed an interlocking. And the first solution was what I call the one-bit manual computer, bâton pilote in French or token in English. You still, there's still some are used if you go to the UK. In some specific lines, they still love to operate like in the old days. You see that it can be a bit uncomfortable. And this token, in fact, was given to the train driver. And the meaning of that bit was that the track is for you. And if you do not have the token, you cannot go on the track. So it was the first interlocking system. It's working, but you will admit that the performance is not optimal. But it was invented at that time. The next step was the mechanical logic. I will not enter into the details. It's very sophisticated, very nice to see. So it's the real interlocking. The name comes from that because you have locking mechanisms between mechanical pieces. So it's wonderful, a wonderful machine. There are still a few in operations, not many. And they were activating mechanical signals, telling the driver, yes, you can go, or no, you cannot go. And it was built in such a way that some mechanical combinations were impossible. So it was a way to enforce safety. With the token, you rely on humans. If the driver goes on the track without the token, you will have a crash. Here, you still have a lot of protections. You have more protections, but the driver needs to look at the signal. It was the first way to provide interlocking functions. The next step was relay-based safety logic. It is using special relays. So a relay is an electromechanical system with a switch. And you need to apply power to a coil in order for the switch to open or close. There are ways to build such a switch so that you can guarantee with a given probability that the switch will not close if you do not apply power to the coil. So you can build gates and or gates by combining those relays. It's a computer. It's Boolean logic programmed by using wiring, connecting relays with each other. You can do anything you want, just Boolean. It requires a lot of wiring. So in stations, you add rooms full of relays, hearing the clicks all day long because the relays were changing position. But it's electrical, so you can start using lamps to provide information to the driver. And it is vital, it's safe, because you can demonstrate that the contact of the relay will not close if there is no energy applied to the relay. But if you make a wiring mistake, problem. If there is a problem in the wiring, you need to find a problem in order to repair, so it's a bit unreliable. There are some that are still in operation. No one wants to open the door because if you open the door, everything will stop. And it's quite expensive. One switch costs typically nowadays, if you take everything into account, 1,500 euros for one switch. But it was an improvement. It was an improvement. Relay-based safety logic. And in the 80s, we managed to connect computers to the relay logic system. So the safety logic was done by the safety relays, but the supervision, the management, setting the routes for the trains, monitoring the position of the train was digital and based on computers. But the computers were not yet able at that time to provide safety integrity, critical functions. It was just monitoring and interfaces. So when did it start to really become digital? It was more or less in year 2000, a bit before, and started in the 90s, in fact, where people thought about how to build computers that can provide critical functions, for which it is possible to demonstrate that they will not fail in such a way that they can be unsafe. So it started at this period of time where we started to deploy those vital computers, for example, here in Belgium, and the logic was programmed into prompts. You were, let's say, writing in the prompt the equivalent of the relay circuit, if you want, and the computer was elaborating the equations that were the equivalent of the relay logic. How was it safe? It will come in. At that time, I was still wearing a tie, as you can see. And it was monitored by computers. This is what you will see if you go today in a control center of Infrabel. It's called EBP. It's the system that is monitoring the train operation that allows to set the routes for the trains. And it was interconnected to a digital system. And it started to deploy in Belgium in the year 2000. I'm not yet saying how it works. I'm just describing how it is implemented. And once you have a computer into a station and you have the supervision system, you still need to drive the objects. So this is the slide you have seen before, but it allows to make the link. You need IOs in order to sense the track, in order to manage the track, switch on and off the lamps of the signals, move the point machines. It needs to be done while demonstrating the safety integrity that I showed before. The point is moving under a train, you will have a derailment. If you show a green light or it should be red, you will have an accident. So all that is part of the critical functionality of the signaling system. So you need computers, which are vitals, you need IOs, which are vitals, communication mechanisms, which are vital, in order to achieve the safety objective. So this is the current situation. So this was the interlocking. So all that will allow you to manage the infrastructure, make sure that you can show a traffic light to the driver that tells him, yes, you can go, no, you cannot go. The points will be in the right position, but still the driver could not respect the red lights or could not respect the speed limit, like in the curve in Saint-Jacques-de-Compostelle. So you need speed enforcement. There are question marks about what is the integrity of a human. I remember the objective of one mistake every 1 billion hours per function. What is the integrity of a human? There are debates about that. Some say that it's in the order of magnitude of 10 to the minus 4. One mistake per 10,000 hours. And I'm down, I think I will do maybe more mistakes than that. But it gives you an order of magnitude. So for sure, you cannot rely on a human to achieve that objective. If you have a human responsibility into the sequence of responsibilities, it will not. So speed control. So the first generation of speed control, it's an example, there are different variations, but it's one that has been deployed in Belgium. It's called brush crocodile, just translate it. So the crocodile is this stuff that goes behind the rail, and the brush is on the train. And when the brush is touching the crocodile, it gets a voltage, a polarity, in fact, which can be positive or negative, against the rail which is connected to Earth. And it says to the driver, if the signal is green or red, basically, and the train potentially, with the most advanced system, could brake if the signal was red. So we know that the train should have stopped. So the train has gone through the red signal, but did not stop. but it will reduce its speed. So it's a first step, but it does not yet prevent the trains not to stop at red signals. To do that, you really need to manage the speed. So the European countries developed systems that were more advanced than the brush and the crocodile. And instead of giving just an information the signal was green or red, they started to develop digital systems that were able to stop the train at a red signal. In order to do that, you need from the infrastructure to send information to the train so that the train can compute a speed profile, maximum speed that shall not be exceeded, otherwise the computer shall break the train to stop at the red signal. And historically, every country developed a solution, and they were all different. So if you take the Thalys, the first version of the Thalys, still a bit like that. In order to go from one country to another, you needed 7 different systems installed on board of a Thalys, and you had to switch automatically or manually from one system to another every time you were changing the border. So the idea was to provide interoperability. Interoperability, the objective was just not to improve the safety compared to national system, to make sure that the trains can cross the borders. So you need one system that is interoperable across Europe. Any train from any manufacturer in any country can drive on any track. So there was a standard that was designed in Europe in order to give information to the driver on a screen in a common format in every country, and common mechanisms for the track to talk to the train, that the train anywhere could get information from the track. I will not enter into the details. There are different mechanisms, the different ways, let's say, or different levels in the system, from the most basic one, where you have tags on the rails that can be read by the train at a speed of up to 500 kilometers. A tag is like a badge, but you need an antenna on board of the train to read the tag and get the information for the tag on the maximum speed. The most advanced system is with a continuous connection between the train and the infrastructure. So the train calls a server using the GSM technology in order to get its movement authorization from the server. So continuous connection between the train and infrastructure by radio. There's a third level which provides, let's say, which is the real target, in fact, because it allows to eliminate some part of the infrastructure and reduce the cost of operation, but I will not enter into the details. So the norms created a standard in terms of DMI, driver machine interface. Any driver on any train in any European country can drive the train by looking at the screen that will provide information in a common way, which is the maximum speed, what will occur in the next kilometers, a lot of information that allows to drive in a common way. And the second standardization is the air gap, a way to transmit information over the air in different ways, continuous or punctual, so that the train can go anywhere and get information. So how does it work? And I will accelerate a little bit. So I will describe what you have on board of the train and in the trackside in order to operate. The first, these are the important wordings. So RBC, Radio Block Center, it's a trackside server. EBC is the onboard computer on board of the train, and DMI is the driver machine interface. So if I use it, you have the meaning on the slide. So the first thing is to be able to read the tags. And the communication is not continuous. So this is how the tags looks like. They are gray in Belgium, so stuff like that goes between the rail. Special tag for rail application, and you have an antenna on board of the train that can activate the tag, provide energy in order to read the content. First portion of the system. Then, if you have a continuous communication, you need a mobile in order to call the server. The mobile is redundant because you want high availability. You can switch to the other one. So this is the mobile that will allow you to call the server that is typically located in the control center. Then extra equipment in the system, you need a computer. It's called the EVC. So every train has a vital computer, a critical computer that will calculate continuously the speed profile that could be respected, that should be respected in order to meet the safety targets. HDMI, in order to give information to the driver, and a juridical recorder, like on aircraft and so on, in order to be able to find it in the getting crash, but there is no crash. So typically it is used to collect information that is used for predictive maintenance. Then you need to measure the speed of the train, because if you want to make sure that the train does not go too fast, you need to know which is the actual speed of the train, and you need to do it in a way that you can guarantee that your measure is correct. So how it is achieved is done by sensor fusion. So you use different types of sensors from different technologies, and you combine the information from the sensor in order to measure the speed. One of the sensors is the wheel sensor. So you measure the rotation of the wheel. Remember what I said at the beginning. It is the best one by far. But a train wheel is in contact with the rail. And if you have a slip or slide effect, the rotation of the wheel is not the image of the actual speed of the train. Because you don't have a correct friction between the wheel and the rail. So that's why you have radars, you have accelerometers, different types of sensors in order to achieve the integrity. So this is how the system looks like, just as a kind of description. Now the last part of the workshop is to explain how can you achieve such an integrity with a digital system. So this is where the embedded system become critical, which means that you can demonstrate a safety integrity. Question?
Are there European countries that use the European standard?
Which ones?
Are there some
There's some that use it or not use it.
that use the European standard that are not in Europe? So let's say.
Yes, that's a good question also. Yes, so a number of countries in the world have decided to adopt the standards. So, for example, we are deploying in South Africa, in Australia, 20 of different countries. China got inspiration from the European standard. They created the Chinese standards, but it's a kind of copy. In the US, it's a bit deployed, but not quite. They developed something which is specific, but yes, the European standard has been adopted in other countries, which is a great opportunity for the rail industry because we can deploy our systems outside of Europe as well. So how does it work? A critical function is implemented by an embedded system. Function is implemented by the embedded system. That's important. So what does it mean? As I said before, the embedded system is in fact made of a processor, something that will perform some logic, that will process inputs that are acquired by sensors, and it is connected to drivers that can activate physical actuators. You see two examples of sensors on the train, a wheel sensor, the antenna, and there you have a brake valve. If you want to brake the train, you must activate the brake valve to brake it. So it's a typical embedded system arrangement. Input sensing, processing, output activation, the cyber physical system. So it means that such a system, in fact, is made of hardware and software. If you want to make it safe, you need to look at both. You need to look at both. Because as you will see, both could have effects on the integrity. That's really important. Everything is a matter of acceptable risk. I wanted to show this picture. Do you think that this would be acceptable in Europe? It's Bangkok market. You should go there. Tourists go on board of the train to see it. You see people are hiding when the train arrives. There are accidents, but they accept it. They accept it. So it defines the level of acceptance. And the first thing that you need to do when you say that something is critical is which is what I will accept or not accept. So if you go back to Europe, this is a bit closer to what we have. You want to relax on the train, and you do not believe that you are taking any risk when you travel on the train. And I remind the objective, less than one serious accident in Europe per year. So starting from there, you can define what you accept and what you do not accept. So which is the level of risk and which is the consequence. If something happens rarely and the impact of it is negligible, nothing will happen, nobody will be hurt, it will be more an availability issue, you don't care too much. If something is frequent in the opposite, and if it creates a crash, people will be dead because the train is going at high speed and it will crash, it's not tolerable. So by looking at the risks, by looking at the level of tolerance, you can define where you are okay and where you are not okay, meaning that your system must be able to protect you. And it is starting from this type of table that in the European standards, you can define target safety integrity level, SIL, safety integrity level. They are equivalent in other domains of the industry, but it defines for one function, which is the acceptable level of risk. And typically, if you take a digital system that will manage the safety of a train, you get the top requirements, because if it fails, if it does not detect properly that the train is in overspeed, if it happens once per month, and if it creates dead people on board of the train, it's not tolerable. It's not tolerable. So this is how, by starting from what is acceptable or not acceptable, through a risk analysis, defining your level of tolerance, you can define a quantified target. And quantified is important because you will need, along the process, to demonstrate that you can achieve that quantified target. So a train critical system will have to meet the highest safety integrity level, it's called SIL 4, where every function must achieve a probability of behaving in an unsafe way of less than once per 1 billion hours. So everything starts from what is acceptable or not acceptable. Yes.
So when you have such very high, well, very low rates on tolerance, how do you validate that? Because you can't just run your system for
No, of course not.
Check that.
This is in the next step.
All right.
Dépasser 10 minutes. I will come to it. If I did not answer your question, you will ask. I will give you a high-level explanation. So in Europe, there is a target. There is a quantified target. So if there is a target, it must be enforced. There are norms that you have to respect, which gives you the rules of the game. So these are defined into Senelec standards. There are different Senelec standards, but these are those that have to be applied in the rail domain, and they define how to demonstrate the safety of a rail system, how to calculate the reliability, availability, maintainability, and safety. How to define a safe communication system, how to design a software. Okay? So these are norms that we have to respect, and other domains of the industry have their own norms. But it is important, this is in this norm that you will see the figure that I've shown before, 10 to the minus 9 correspond to C4, and it tells you what needs to be done. More or less. You have to invent a few things yourself. So what is the fear with a critical system? If there's no bug, if everything has not been done correctly, it will do what it's designed to do. What you fear is a failure. Something goes wrong. So first, a definition of the possible failures. I've taken example in the car industry. Not in the car industry really, but in the life. First, random failures. What is a random failure? Random failure is something that breaks. You don't know when it will occur, but anything you have, your mobile, your car, your computer, one day will break. You don't know when. Something, your keyboard, your power supply, something will break one day. It's just physical. Everything breaks. So it's a random failure. It's a typical example of a car manufacturer not choosing Asian components. So the car is unreliable. It breaks. But in fact, the function that you expected, which was to go from A to B with your car, cannot be implemented because your car is broken. It's a random failure. There are other types of random failure that you shall not forget, which can occur. You know which ones? They are not related to the car itself.
Design failures.
Next step.
People said the weather.
The weather.
Weather, you said?
Yes.
Yes, the environment. The environment. Things can happen that are external. You don't know when. It's a random failure, but yes, the environment will have impact on failures. You can no more operate your system. So how to protect against random failure? What do they impact, in fact? They will mainly impact the hardware. The hardware causes random failure because it breaks. Software does not break. Computer will break. Can fail. But I will come to it. So how do you protect against random failure? See a nice picture, but I've got the board with me. So I will not circulate it, but you will be able to see it afterwards. You see the one on the picture. Exactly that one. It was designed 30 years ago, but it's big enough so that you can see how it is designed. There are different ways to do it with computers. I describe a subset of them. Those are, let's say, the easiest to understand. A typical way to do it is using a 2 out of 2 architecture. It's called a composite fail-safe architecture. And you understand what it means. You've got 2 computers instead of 1. They are doing the same thing in parallel, and you compare the results. See there the 2 microprocessors on the board, 2 identical circuits, one on the left, one on the right. You compare, and if they both come up with the same results, you consider it safe. When? That's the start. really the start of what you need, which means that you will have two channels. Each channel will be connected to the inputs, will potentially have different sensors. You will process drives, you will have two output activation mechanism, and you will drive the actual outputs if the two channels generate the same results. Okay. You do that, you need a piece of software. You need a piece of software, which is a kind of operating system, but it's a special operating system because it's a multi-processor operating system, not the way you would think it on your PC, not to share the load between cores, but really to make sure that you manage the fact that you are in a multi-processor architecture. So, for example, if you want the process to come up with the same results, if you are sensing analog inputs, there's a high probability that you will not measure exactly the same thing. There might be just a bit difference in the analog converters, or you will sample the input with a little time difference. So if you enter into the process and generate the outputs, for sure the outputs will be different. So you need some kind of voting mechanisms between the inputs that are sensed. You need comparison mechanisms between the processes. So the system might be operating system that comes on top. It is not yet enough. It is not yet enough because failures will occur. And you need to stop the system when a failure occurs. You need to react. So you need mechanisms in order to detect the failure, detection, and stop the system negation. So for example, you will implement into every processor built-in tests to make sure that continuously you test that your processor is okay. For example, that you are still able to write in the RAM and to read in the RAM. On a regular basis, you will test your RAM and will write, I don't know, FF 1050 and then 00. Test all the bits values to check that I can do it. And my operating system must allow me to stop the output. Because if a failure occurs, and if I let it go forever, potentially there will be a mistake, there will be a hardware failure, and I will still activate the output because the failure has not been detected. So this operating system is there to detect the failures of the hardware and to react in a way that will make sure that you negate, so which means that you stop your system in a guaranteed way. So for example, and you will see it on the board later on, there is a fuse on the board, a physical fuse. It's a bit old-fashioned, but it explains well how it works. If a failure is detected, the operating system will blow the fuse. And if the fuse is blown, you cannot activate the outputs anymore. It's an example of a very practical solution on how to make sure that you can isolate the output. And to do that, you need the two channels and you need the operating system at system level. Well, what can be achieved with that? If I look at one channel, the lambda value is the failure rate of the system. So when you have a hardware, you have a processor, you have electronic components, you know how much it will fail. It's available in books for a transistor, for a processor, depending on the number of gates, the complexity of it. It has a probability to fail. The more complex it is, the more it will fail. So you can calculate by building a fault tree how much your system will fail. I will explain is a simplified version of it because not all failures of the hardware will lead to safe event. I consider that all failures potentially can lead to an unsafe event. The probability of failures of your hardware is called lambda what I've shown there, it's 10 to the minus 6, maybe, I don't know, order of magnitude. So it does not reach the objective of 10 to the minus 9, explaining why you need a second channel in parallel. What can I achieve? The second channel, if it is identical, will have also a failure rate of lambda. If the time to detect the failure is t, during a time of t, potentially I have a failure that is unknown, and I could have a behavior that is unseen. So there is a formula that shows that in such an architecture, tolerable as a rate, 10 to the minus 9 in my case, that can be achieved is proportional to the square of lambda. Nice. 10 to the minus 6, square of it, 10 to the minus 12. Yes, I achieve it. But I need to make sure that t, expressed in hours, is small enough. When I test my RAM, I do not test my RAM continuously, otherwise my processor will only do that. So it's a slow process. Maybe it takes 1 day to test the full RAM to write in every location of the RAM. So t might be in the range of a few hours. But if t is too high, I lose the benefit of duplicating my channels. But that's the concept of it. By having 2 channels in parallel, I can reach something that is in the order of the square value of what can be achieved with a single channel. Orders of magnitude is not completely accurate, but it gives you the flavor. Provided, don't forget the rock on the car. Provided I'm protected against common mode failures, which can be of various types. So some will tell you they're using the same processor. So they could potentially react exactly in the same way. There is a glitch in the power supply. Okay, so I will desynchronize a bit my processors to make sure that if there is a glitch on one, there is no glitch. Just an example. EMCs. What we do with EMCs? You will see on the board, I've removed the cover so that you see the processors, but in fact, the processors are in a closed box. It's completely closed and protected against the environment with a shielding. All signals going in and out are being filtered. So it's a very special design. Channel A and B are completely separated. They are supplied from different voltages. So a lot of protections need to be put on top in order to be protected against common mode failure. EMC is not minor. If you take a rail application and you think about one of the worst problems that you could have along a railway is lightning. Lightning is a lot of energy. And in fact, when you have lightning in the area of a railway track, the lightning goes every time on the catenary mast. It goes from the mast to the cloud. But it means that it injects energy into the rail system. You will have over voltage and plenty of perturbation. So you need to be protected. I've described this operating system at a system level that usually you need to write yourself. You cannot buy such an operating system. Yes, there are vital platforms that you can buy from the market. It's appearing, but typically, if you want your own optimized computer, you will write your operating system yourself at system level. You can be supported by operating systems that run on the processor itself. And there are some operating systems at processor level, like PyCo is just an example, which provide some services that can be demonstrated and that can help you segregation, allocation of certain portion of the RAM to some of the tasks. This can be done by implementing such an OS on the processor, but still you will need the system layer. But you can be helped with some modern operating system which come on top of conventional operating system and provide extra services. And if you want to reach the full availability target, because if you stop the computer, potentially you will stop the train. And the computer is the server that connects to all trains. If you stop the computer, you stop all trains. It is not acceptable. You need availability. So there is a brilliant trick in order to achieve availability on top of safety when you have composite safety. So you have multiple computers. It's not a 2 out of 2, it's a 2 out of 3. So if 2 computers agree, you can work. So if one fails, and you still keep the operation. So you can build CPU boards with 3 computers on it. That's a 2 out of 3. So this is a fault tolerance, critical CPU with fault tolerance. If it fails, the system goes on. It's another one, it's not taken. That one, the 3 processors are on the same board. It comes from an onboard computer, again, 13 years old. This one has 3 different CPU, and you see the MP board, this board. It's just an industrial computer. It was designed by Alstom. But the arrangement and the operating system is designed by Alstom. But the CPU itself is bought by Alstom. Lot of free arrangements. This was for random failure. Yes, I will stop. It's nearly the end. Then you have the systematic failures. Someone mentioned the conception failures. So the mistake that you made by designing your system. We are getting closer to the software. A bug is a systematic failure. If you go through a certain path in your software, if the bug is there and in the conditions are met, every time you go through that path, it will occur. It's systematic, not random. Some examples, again, using the car. It's a design mistake. It's a design mistake. Another one, not a car this time. Whoops. It's a design mistake. So how do we protect against that? You cannot do it by just duplicating. You need something else because a mistake is a mistake. So what you need is a process. If this guy had a friend telling him when he bought the car, your car will never go into your garage, wide, or telling him you need a wider door, or when designing the drawer, able to open the drawer, if someone had tested the drawers, it would have been detected. So the standard standards tell you how to do it, and it tells you 2 things. You should be organized in such a way that you will detect your mistakes, and you will need to apply processes, methodologies that will allow you to detect your mistake. So it's a matter of organization and processes. I give you here an example, independence. Independence. Remember what I said with the garage? If the guy had a friend, he did not think that the door was not wide enough, so someone else should have told him. So when you design a critical software or a critical embedded system, you need an organization where you are independent. You have someone else with a different brain that will somehow check what you do. I don't like it, but it's a way to say it. So those validating that what you did was correct must be independent. It's a different part of the organization, different people, and they will be there to check that what you did is correct. And on top of that, there is an independent body that will assess that everything you organized was correct. So that's independence is part of the solution. Then in terms of process, again, there are variations of that. But the core is the V cycle. And the V cycle tells you that in a process where you want to reach high integrity, you start with your system design, you split your hardware and your software, and for each of them, you have a V cycle. When you go here, you have designed your solution, your hardware and your software, and here you validate it to check it that what you did is correct. I do not enter into the details of the document and the steps. What I want to insist on is that it doesn't mean that you have a team designing something without caring about the results, giving it to a friend, test it, look at it. It doesn't work. If you do that, and if it is detected by the independent CTF assessor, you are dead. The quality must be ensured by the left branch. The designer must guarantee that there is no bug or nearly no bug. It needs to perform the designer test to achieve the quality. The validation must come on top. Otherwise, you will never achieve the results because you rely on the testing, on the experience of the validator to detect the inadequacy. You need the quality on top. The quality needs to be ensured in the left branch. So do not misunderstand the meaning of the V cycle. You still have to work correctly in the left branch of the V. Then what does the CNLX standard tells you? It gives you recommendation on techniques that have been acknowledged as applicable to the design, many of those critical software. There are plenty of tables in the norms. I will not go into the details, but I give you two examples. For example, one of the most recommended language is EDA. It's not the only one, but it has been used for years and years for the design of aircraft computers, of railway computers, because it has some embedded functionalities. The compiler has some characteristics that can be used. But you can use C, you can use Java, you can use Pascal, you can use Basic. You will be able to use it in the future. It's appearing progressively. Okay, but there are recommendations. There are recommendations on the way you code. The defensive coding approaches, with things that shall be done or not done. This is written in the standard. And it is by applying the standard that you guarantee that your software is correct. Fortunately, new techniques are appearing. Yes, within a V cycle, it's possible to have an agile mechanism with Scrum technologies. It's possible, yes, in the left branch of the V. Yes, progressively, you can use modern techniques that allows you, for example, to model your spec and progressively generate the code. Yes, it's possible, and it is acknowledged even as sometimes better than textual language, because you can start from a model of your spec and perform analysis on the model all along the process. Here also, yes, it's appearing progressively into the design of systems, provided you use the right methodologies and you respect the process. Last slide, remember. A matter of complexity. What I have described, okay, is basically simple, but we are talking about complex systems. Here I take a very simple example of code. If you look at it, and if you can loop 13 times into such an algorithm, there are in total 1.5 billion ways to go from in to out, depending on the way you go your software. So if you want to validate, if you want to check that your software is okay, potentially, you can imagine the number of tests that must be done. So in practice, it's not possible. You need to divide your process into multiple steps so that you cannot go through all the paths, or you do it by modules, or you are supported by tools to do that. It gives you a flavor of the complexity, because if you take that computer, which is the onboard computer, and checks the speed of the train, it does a lot of things on top of that. And it does that just to give you a few figures. 500,000 instructions in the software. When we perform a validation, we have 10,000 functional tests to perform, and it takes 9 months. Despite the use of some automated tools from different steps in the process, still the testing, the functional testing in the lab with the real hardware and the real software is key in the process, and is one of the complexity of such a development. So if you like it, but you would like to know more, no, that's the last one. Which sectors of the industry? We mentioned some of them. The expertise of Alstom in Belgium is coming from the nuclear plants because the ASEC in Charleroi designed the PLCs that are controlling the nuclear plant in Belgium. This is how we gain expertise in vital systems, because the objective for a nuclear plant is the same as for the railway. It's the same order of magnitude. The aircraft I mentioned is the same job to design a flight computer, except that you can stop the train, you cannot stop the aircraft. So in the future, normally I ask the question, but I'll give you the answer. These are domains, my friends from LHI will soon adopt. Cars will become trains if they want to be autonomous. And we get inspiration from the technologies of the trains to be fully autonomous. For example, they will be guided on motorways or get information from the infrastructure. The drone cannot fall on your head. The drone is flying on top of the city. You need to guarantee that even in degraded mode, there will be sufficient protection. Surgery. Surgeons are more and more supported by robots. The scalpel is managed by robots. You can imagine what happens if the scalpel does what it wants. So you need some integrity of such devices. So what I've just described is currently a bit specific to the domains that I've shown, but will progressively be applied in other domains of the industry. So if we dream of that, if you start loving it, as I do, we decided to do something and to create a specific certificate in critical embedded system. I've been working on that for many years. So it will be available here in Valanov. It will start in January. So it's an inter-university certificate. So combining the skills of the academic, let's say, side and of the industry side. So we have a kind of consortium. The core is UC Louvain, VUB, Eschin, and Alstom. But we have partners from other schools and from other industries. And the idea is really to provide a specific program that tells you the full story that I summarize in 15-20 minutes for this inter-university certificate, and it's 19 CTS, it's correct. 22, okay, 22 weeks. So I encourage you, if you have been interested by what I explained, think about it and register once it will be possible to this inter-university certificate. That's it. I've got the boards there, so if you want to see them, have more explanation, you can come to me, but I stop there, otherwise I will completely explode the timing.
Thank you.
Thank you.